Yes, okay. Cool. So, yeah, so last time, we had a crash course in statistics, and basically, one of many, many ways of viewing things is that we have a system where we have observations y, there's a hidden process z in the background, and there's a parameter theta, which is a parameter for a model. And so the, we have a model here, parameterized model. So there's a p of y given theta and a p of complete data given theta. And here's the maximum likelihood estimate where you find the theta that makes the probability of your observations is the largest. Okay? It's a very reasonable thing to do. And there's all sorts of nice properties. And then a procedure to try to solve this maximization is EM, where you do these two steps. And I wish I could give you a better feeling of how they came up with this crazy idea. I'm sorry, I feel like I just haven't done my homework properly. I imagine it came out of a particular example, because as we're going to see for hidden Markov models, it's so natural and beautiful, but I just don't know. And I've taught this, this is the third time I've taught this algorithm, and every time I feel guilty at this stage that I forgot to do my homework. But anyway, there's this mysterious step here where you take your previous model estimate and take an expectation of the log likelihood. That's what this is. It's not a likelihood ratio, it's a log likelihood based on your previous model. Okay, and again, the observations, I keep saying this, the observations were obtained, put in memory. Every expectation is conditioned on that, okay? That's it. And then you take your new parameter by maximizing this. All right, so it's a big hack. What I love about this, so it may be obsolete even, but it's so awesome in terms of teaching, because you can illustrate all sorts of concepts. I don't think it is obsolete, but there are lots of competing algorithms, but the main reason I go into detail is because you just have all sorts of concepts you can talk about, right? If all I knew is I could just state this algorithm, walk away, I wouldn't do it. I'd just say, go look at Wikipedia, all right? All right. Oh, yes. All of you have been eagerly waiting for the homework. I told you I'd be giving you homework every week, and I'm sorry I disappointed you. So if you want me to, I can make homework due on Thursday, or we can just forget that plan. And the last homework assignment will be due on Friday next week. And basically you'll be applying EM and playing around with this. Okay. Mainly just, our teaching assistant and myself are overworked as well, so we just haven't had time to. And we're trying to come up with a really nice sort of laboratory experiment with EM, and we're based on previous versions of this course, and we just haven't been able to polish it up yet. So we'll be launching that soon, maybe tomorrow or the next day. But you guys will procrastinate anyway, so if we get it to you on Friday or Saturday or Sunday, you won't start till Wednesday anyway next week, all right? Thursday after the exam. There's an exam next week. Okay. All right. What's that? It's next Wednesday. Next Wednesday. You'll get information soon. All right. So basically today we're going to talk about understanding it. Basically, does it converge? And it sort of does. In some sense it converges. And also we're going to go and just go through and apply this to hidden Markov models. Okay? Okay, so the Baum-Welsh algorithm is just EM applied to hidden Markov models. Okay, so let me review what we did last time. So yeah, if I could do it that way, yeah. put this in quotes. It's just a general fact, that we can factorize a joint distribution as a probability of a marginal plus a transition probability, right? And that's why we always have this factorization. So just to introduce the notation last time, this complete data here yeah, let me write, I'm going to use, sorry. Okay, and so then we have this notation. So we take our complete data, we write it as the likelihood that we had before, plus some sort of kernel, which is this transition thing here. And I'm going to stick to probability mass functions, so this is all completely trivial. Just discrete random variables. There could potentially be issues if we had densities, things were singular and stuff like that. But if it's all probability mass functions, this is just a division. This is this is defined to be this divided by this. It's just it seems pretty simple if it's all discrete. Let's see, what else do I want to say? So then we can go through and play around with this as we did before. What's that?
I need to scream something.
Scream? He wants to scream.
Shouldn't it be X and Y given data for complete data? You factorize it?
No, it's X is Z and Y.
No,
Yeah.
for that line.
Yeah, I mean, looks good to me. I just rewrote down this. Oh, I see. I'm sorry. Oh, yeah, absolutely. Thank you. No, you didn't have to scream. That was just a typo. Oh, wait a second. What am I doing? No. It's just No, sorry. X. No. It's just the fact that I'm putting these guys together just to remove two symbols. That's all. So X was defined to be Z and Y. That's all. Yeah. So Y's in there. So they can go through and you can plug all this in, and as we did last time, and I'll just write that down again. Was there a mistake here? Well, yeah, it doesn't even matter. You see, X, it just doesn't matter. I mean, you're absolutely right. I could write Z given Y, or I'm just going to stick to what I'm trying to do is stick to the notation in the text as closely as possible, and so and that's what he used. Okay. Yeah. So whether it's whether it's X and Z or X or Z here, doesn't matter. Yeah. All right. I'm just trying to stick to the notation in the book. All right. Yeah. All right. So So let's do it. Okay. So you take this and you plug this in, and oh, no. Here's a mistake you guys should have talked about. Fuck. Damn. No. All right. So basically, there's nothing random here a moment ago. I had a Y in there. So X is distributed according to the model with parameter theta k here. All right. So then, I hate to go through this all again, but let's do it. So I get the expectation of this log now is the log of this. It turns into a sum. This is correct if I put a 1 there, but I'm going to divide by Okay, so we did this last lecture. Basically, what I've done here is I've taken the log of this quantity here, and that's why I've got a log of that. I've got a log of this term here, which is that. All right, but I divided by this funky thing here, and then got rid of it. So these two terms are identical, but different signs. They cancel out. You know, log of 1 over blah is minus log of blah, right? And so this expectation is a relative entropy, except there's a minus sign missing because I'm taking the expectation with theta k, so it's flipped around, all right? And this is the expectation of a log of a probability mass function with respect to that probability mass function. That's minus entropy. All right. You know, this k here is a probability mass function for any y and any theta. So this is again. So this is equal to the log of p of y given theta minus a relative entropy. And then minus what I'll just call hk. You know, it's the entropy of the of this weird complete data PMF, a transition matrix with respect to the kth model. What's that? The what? Yeah, everything here. I'm going to stick to PMFs. So for each, so you know, x will be discrete. X, you know, z is discrete and y is discrete.
So k is not. K is further.
K is a matrix here. It's a matrix. It's a transition matrix. I mean transition matrix. It's not. There's nothing Markov here. I mean, right here. It's just, you know, the probability right there. I mean, it's the same as what I've written down here, just to make things concrete. Yeah. Yeah. And obviously, since x is just z and y, one thing is fixed once you know y. Yeah. All right. Okay. So you know, relative entropy pops up where you least expect it. I mean, for me, it really is. It comes up all the time. Yep.
Sorry to go back to that issue earlier.
Yeah.
X is still equal to y.
Yeah. No, that's right. I'm just copying the notation in the text. I just want to be consistent.
For your k, x given y, what does it mean for y given y?
Oh, it just means if you're given y, it's y. Yeah. Yeah. It's just, yeah. Okay, it's just, that's all.
So you're saying
It's not useful. We could have used z. You know, I mean, once you know, the probability that zy is equal to z prime y prime given y equals y. This is a waste of time. We shouldn't be doing this. Well, anyway, it's equal to the indicator function that y equals y prime times the probability that z equals z prime given y equals y. Right? I mean, you know, big deal. So it's really, it doesn't make no sense at all. As I agree with all of you, to put an x, that's what the text did, and I just wanted it to be the same. All right. So, but all this structure is really important, and so once again, you would never use this for computation. It is only for analysis, because the whole point of EM is that this is an ugly monster, right? You know, and it turns out, I mean, and this is not. You design things so maximizing that is easy, while maximizing that is hard, all right? And so you will see that for Baum-Welsh. And applying this to hidden Markov models, maximizing that's trivial. Maximizing that directly is insanely hard. Yes?
This is a really dumb question.
No.
But like,
Dumb question.
why does that theta not have a k? Is that like the theta that is optimal?
Where?
Or is
No, it's a variable. But where?
Thetas that aren't tagged with k.
No, theta k, this is a recursive algorithm.
Yeah, so I know, like, so we're updating theta, right?
Right there.
Every iteration we update theta.
Yeah.
But then, you know, like,
We're trying to find that
there's
function.
thetas that don't have k's on them. So
Right there. Take a look.
I'm concerned.
Take a look. Look at EM. So EM, I define a function of theta. You know, for every theta, I compute this expectation, and I come up with this function, you know, which sounds pretty wacko nuts. For every theta in Rn, I will have to compute an expectation. And then I go through and I have to then perform maximization, right? So it's nuts. It can't be done. So you have to get lucky. So as we will see hopefully today, for hidden Markov models, you can compute this in closed form, and you can compute this in closed form, and everything's beautiful. And in general, you'll have to use stochastic approximation. You won't compute this expectation. You'll take the gradient, set it equal to 0 or something, and then use stochastic approximation to try to find the zero, points where the gradient is 0. You know, and that's why you got a tutorial by Aditya ages ago. So you could just use stochastic approximation instead. And I don't know if that's common in practice, but that's one thing you can do. But the thing is, again, what's so cool is that EM then turns out to be ML with regularization. I said this last time. You know, it's just so this is like an example of regularization where you put in a penalty term to make your new, to make you not stray off from some previous value. And people do this all the time on purpose to make algorithms nice. The examples where by designing a regularization term appropriately, you can get really beautiful performance. It's amazing that it just comes out by luck. You know, it just appeared by luck. It's really just fascinating that relative entropy just likes us. It just pops up out of nowhere, you know, like Dora, you know, and a monkey. All right, so let's put this to use and see what we get from it. Okay, so one thing we get from this is a lemma. That if you look at P of y given theta k, so you look at the likelihood at time k with your kth model, it's actually increasing, well, non-decreasing. And I think the proof is one line. Let's see if we can do it in one line. Do I dare? Nah, is it too dangerous? Hold on a second. Okay, let's do this carefully. So first of all, I've got an inequality here. Where did I get that inequality? Somebody tell me. What's that? Great. Okay, so using the fact that this is grade equal to 0, I can throw it away and get an upper bound. So when I plug in theta k plus 1, that's the maximizer, then this would be equality if I kept this relative entropy term, but I dropped it, so I got something I mean, hold on a second. This is the wrong direction, you jerk. You were telling me relative entropy is negative. I mean, it's positive. Okay. All right, so you take this whole thing and you throw away this negative term, you'll get something bigger, not smaller. All right, now how can I get a lower bound on this? Anybody have any suggestions? So theta k plus 1 is a maximizer. What can I drop in and get something informative? You know, so I've got this this max step. So you know, if I want to get some sort of bounds, what can I plug in for theta? Remember, I'm trying to show this is, you know, I'm trying to compare this with the log of this. So I can tell many of you know the answer. You knew already, and you, theta k, yeah. So it's greater than equal to qk of theta k. And I know a lot of you wanted to say it as well. I know a lot of you did. And what happens when you plug in theta k, you get this. And here you get the relative entropy of something with itself, which is 0. And then you get your friend minus hk, which is sort of like the monkey. Entropy is friendly as well, right? 3D. So the entropy terms are just common; they cancel out, and I get this is increasing. So it's really, that's the first sweet thing you get, is without any thought at all, you get that the thing is monotone, all right? All right. So you can imagine that seems to suggest the parameters might converge, you know, because given that these are increasing, at least these guys are now convergent, right? You know, as k goes to infinity, you know, you've got a monotone sequence. It can go to infinity. We're going to assume that away. But this is a monotone, non-decreasing, so it's convergent. Okay. All right. Yep.
If you're saying this because you're saying that qk of theta k plus 1 will always be greater than qk of theta.
Well, that's what I'm. So lemma, this is non-decrease. It can never go down, and the proof is right there because I have this is greater equal to this.
Why is it that theta k plus qk of theta k plus 1 is greater than qk of theta?
No, here. Oh, yeah. This is the fact. It's because it's the max step. Theta k plus 1 is the maximizer. Yeah. Okay. All right. So we can't prove convergence. So we can't prove convergence, but what we can do is we could look at any possible subsequential limit or subsequence of the sequence and obtain properties of that. And we obtain some really sweet properties of these subsequences. I'm sorry. I screwed up my language. Actually, can you erase everything I just wrote down? I don't know, there was something funky in my notes, and I wrote it down. I don't. So a subsequential limit is defined by taking a subsequence of the integers, which is non-decreasing, and then taking the limit as I goes to infinity. And we can get really nice properties of any possible subsequential limit. Right? So we don't know. So basically, the sequence converges if there's only one possible subsequential limit. You know. Okay, I bet there are examples out there where it doesn't converge. You know, I don't know. I mean, it's a big literature. Okay, so here's a beautiful proposition. Assume a bunch of stuff. So see the book. So this is proposition, what is it? Anyway. So there's one proposition in the textbook, and there's a list of assumptions, and why write them all down? Basically, we'll see them as we go along. We need this guy to be differentiable in theta. And this differentiable in theta, and we want this to be positive, and things like that. So there's a bunch of assumptions. When we go through the proof, you'll see, we need differentiability, we need continuity, things like that. So I think it'll be much more instructive to say, hey, we need an assumption here. Right? And this is how you do research. You go through and you hack away and you say, if I assume this, I can get this. All right. You know, assume every matrix is diagonalizable, you can prove anything. That's a secret. But so if you assume a bunch of stuff, then what you find is that theta star is a stationary point. And I want to say this, I want to put the log in there. Well, all right. All right. So what that means is that you take all the partial derivatives of this likelihood with respect to theta, they're all equal to 0. So this is a vector. So the partial of this with respect to theta I equals 0 for each I. All right. Now the proof says something a lot more. You know, the proof gives you a beautiful bound. So what we can end up showing is that, and I don't know why the text doesn't just say this in the front, because it's such a nice bound. What you end up proving is that the thing that you care about, that you almost, hold on a second, yeah. We want to maximize, so this is an annoying extra term, right? What we'd like to do is for this to be bigger than this for all theta. it turns out that we have to add on this additional term, and then we get a maximizer, right? Now this looks weak, right? Because basically we've got this additional annoying term, right? But this term here is minimized when theta equals theta star, and you get 0, all right? So basically this term here is a smooth, nice thing under the assumption of a bunch of stuff. You assume this is differentiable, all right? And we know this has a global minimizer when theta equals theta star. It gives you 0. It's positive otherwise, all right? So why is it that this implies this? Can you see it? Can you see it geometrically? So you've got, basically you're comparing two functions. Definitely need two colors for this. I've got the right-hand side, which is the big fat guy. And a lot of conditions, if this was linear in theta, if this guy were linear in theta, say, this whole thing would be convex, Or if it was the exponential of something linear in theta, this whole thing would be convex. Well, I'd be careful. I mean, under really general conditions, this would actually be convex. I mean, wait. Convex. Yeah, I wrote this backwards. This is a very unusual situation, but I just wrote down here. Let's make it go back out. Anyway. Yeah, because relative energy is convex, and maybe this was linear or something like that. But I've got this big fat thing up here, and then I've got my friend over here, and it's lower bounded, but it meets when theta equals theta star. And I'm a terrible artist. Should slow down. I don't know why I flipped things around. I just had a sign error in my face. You can make it go down if you want. But. All right. Okay, so we have this green thing is less than the red thing everywhere. And for the red thing, theta star is a global minimizer, right? You're all with me there. That thing's fixed. Theta is a variable here. This is always positive unless theta equals theta star. Or it could be 0 elsewhere, but theta equals theta star gives you 0. So somebody tell me, it's just basic calculus. Why is the derivative 0? No. Yeah, well, I mean, it's just a, yeah, I mean, you could just bring this to the other side and take derivatives, you could just take this on the right-hand side and see that it's greater equal to 0 everywhere, is what it's saying. All right, I've got a function. With an iPad, you would take this and move it over and say this minus this is greater equal to 0, right? It's greater equal to 0 everywhere, except when theta equals theta star, I get 0. And so because it's a minimizer, I get 0. So the difference So one, as you said, take the difference, and it has a global minimizer when theta equals theta star. So the gradient of the difference is equal to 0. But the really important thing is that the gradient of this at theta star is also equal to 0 because theta equals theta star is a minimizer of that. Okay, so you need two things, right?